This question is from October-November 2017, paper 22, question 3 is about a spring and pressure. A spring is attached at one end to a fixed point and hangs vertically with a cube attached to the other end. The cube is initially held so that the spring has zero extension, as shown in this picture. The cube has weight 4 newtons and sides of length 5.1 centimeters. The cube is released and sinks into water as the spring extends. The cube reaches equilibrium with its base at a depth of 7 centimeters below the water surface, as shown in this picture. The density of the water is 1,000 kilograms per cubic meter. A. Calculate the difference in the pressure exerted by the water on the bottom face and on the top face of the cube. Let me start with the pressure at the top. Can be calculated by this formula. The density of the liquid times gravity times the top face cube. So here we have values substitutions. The density of the water is 1,000. The value of the acceleration of gravity is 9.81 meters per second square. And the top face cube here is the entire length from the water surface to the bottom of the cube minus the length of the cube. So the multiplication result is 186.39 Pascal. Now let's calculate the pressure at the bottom. So the same formula, but the value substitutions are different. So the density of the water is the same, G is the same, but the height is 0.07 meters, right? Is instead of centimeters, we are doing meters because the answer is in Pascal. So the answer is 686.7 Pascal, and the difference between the pressure top and bottom is 500 Pascal. So that's the answer. Question B. Use your answer in A, 500 pascals, to show that the upthrust on the cube is 1.3 newtons. So the upthrust force is equal to the difference in pressure between the bottom and the top times the cross-sectional area. So we already have this pressure, and the area of the cube is in meters is 5.1 times 10 to the negative 2 times the same value because cube has the same length on the sides. So here is 500 Pascal times the area is square. So the F up or upthrust force is 1.3 Newton. Question C. Calculate the force exerted on the spring by the cube when it's in equilibrium in the water. So it's in equilibrium means that we have to look at the forces acting on the cube. So here we have the weight of the cube and the upthrust force from answer B, 1.3 newtons. Let's take a look at the formula that we need to use. The sum of forces up is equal to the sum of forces down because it's in equilibrium. Let's look now at the free body diagram. So here we have Fg, we have the force acting on the spring, and we have the upthrust force. Doing substitutions, and rearrange for the value of the force acting on the spring, and calculating the value, the force is 2.7 newtons. Question D. The spring obeys Hooke's law and has a spring constant of 30 newtons per meter. Determine the initial height above the water surface of the base of the cube before it was released. So let's understand what's going on. So here is the cube before being released in water, and the second picture shows the cube in the water and in equilibrium. So this height that you are looking for here, the little h, is the height above the water from the bottom of the cube. So we are looking for this number. So the height is equal to the spring extension, and it can be calculated from Hooke's law, right? So the extension, which means this is the initial and this is final. The difference between the length of the spring, the final minus the initial, is the spring extension. So we are looking for this number. To calculate this, we need Hooke's law formula. The force on the spring is equal to the spring constant, K, times the spring extension. So I'm going to rearrange this in terms of the extension. So then we have the force acting on the spring that we calculated previously, divided by the constant, the spring constant that was given in this question. So doing the value substitutions, the x, the total extension of the spring, is 9 centimeters. So now we are going to calculate the spring extension, which is the final minus the initial, right? So here we have the final, which is 9 centimeters minus 7 centimeters that we have in the water. And that gives us the extension of 2 centimeters. So the height above the surface is exactly 2 centimeters. Question E. The cube in the water is released from the spring. Determine the initial acceleration of the cube. When we have forces involved, let's use second Newton's law to calculate the acceleration. So F net is equal ma. The forces acting on this cube is the weight minus F up. Now the direction, if Fg is positive and F up is negative, because the direction the cube is moving in the water is downward. So we are going to make the weight force positive, equal ma. Then we have that acceleration is the weight minus upthrust force divided by the mass of the cube. So the numerical values that I'm using to do the substitutions is the weight is 4 Newton, was given. The mass is 4 Newton divided by 9.81, which is 0.408 kilograms. And the upthrust force from the answer 3B, question 3B, is 1.3 newtons. So direct substitutions, and the answer is 6.6 meters per second square. Question double I. Describe and explain the variation, if any, of the acceleration of the cube as it sinks in the water. We know that F net is ma. So all the forces acting in this cube right now, now that we have drag force, is Fg minus F up minus the drag force, mass times acceleration. So the acceleration now including the drag force, is Fg minus F up minus drag force divided by the mass. If the drag force in the fluid increases with speed, then the acceleration would decrease until it becomes 0. At this point, the cube would fall with constant speed.